Next question is question number 66. The noise with double-sided power spectral density of K over all frequencies is passed through a RC low pass filter with 3 dB cutoff frequency FC. The noise power at the filter output is, we have to find out which one is correct. That is, the noise power we have to find out when noise with double-sided power spectral density K is passed through a low pass filter with cutoff frequency 3 dB cutoff frequency FC. So we have a system, that is the low pass filter, having the transfer function h of omega. We have a power spectral density at the input. We have a power spectral density at the output. Now, what is the power spectral density of the input that is given in the question? That is K, and what is the unit? Unit is watt per hertz. K watt per hertz. Now, it is also given in the question. The transfer function h omega we can easily find out, because the low pass filter is given. The system is basically a low pass filter, RC low pass filter, and its cutoff frequency is FC. We can easily write what is h of omega. H of omega with unit gain we can write 1 by 1 plus RC omega whole square root over. So this is the h of omega. Now if we plot the impulse response of the filter as a function of omega, it will be looking like this, because it is a low pass filter. It will have cutoff frequency omega c, that is the 3 dB cutoff frequency. That is, when the passband gain is lower by 3 dB, we have the cutoff frequency omega c, and omega c is given to be 1 by RC. As omega c equal to 2 pi fc, so you can write the cutoff frequency fc to be equal to 1 by 2 pi RC. Now what is the power spectral density at the output? The power spectral density at the output is nothing but the power spectral density of the input into h of omega modulo square, the magnitude of the system transfer function square of that will be multiplied with the power spectral density at the input, which will give the power spectral density at the output. So we can simply write K into, because this is h of omega we have already found out, so h of omega whole square, if we multiply with K, we will have K by 1 plus RC omega whole square. Now power spectral density we know, we can easily get the power. The noise power at the output is nothing but integration of the power spectral density over d omega, and the limit will be put from minus infinity to infinity. 1 by 2 pi will be there at the outside. If we substitute, then we will get this expression. So if you see, now we will try to integrate this one. Here K is a constant, we can take K outside, and this function is always an even function of omega. So from minus infinity to infinity, we can simply change the limit to 0 to infinity, and we can put 2 outside. So if we put 2 outside and K if we take outside, then 2 will be cancelled. So we will have only K by pi at the outside, and the integration will be looking like this. That is, the integration will be happening over 0 to infinity 1 by 1 plus RC omega whole square into d of omega. If we integrate this, we will have a tan function, and after integration we will get this expression tan inverse RC omega 0 to infinity. For infinity, if we put here omega, then we will have pi by 2, and for 0 it will be simply 0. So if we solve this, we will get K by pi RC, that is K by pi RC, and this will simply give pi by 2. So pi by 2. Okay. If we further simplify this, that is K pi 1 by 2 pi RC. 1 by 2 pi RC is nothing but the cutoff frequency FC. So you can write K pi FC. That is the noise power at the output, K pi FC watt. And if we see among the option C is matching with our result, that is the output noise power. Hence, option C is the correct answer for question number 66. Next, in this question, it is given, consider a binary symmetric channel with probability of error being P. To transmit a bit, say 1, we transmit a sequence of 3 ones. The receiver will interpret the received sequence to be represent 1 if at least 2 bits are 1. The probability that the transmitted bit will be received in error is, we have to find out. So we have at the transmitter for 3 1 bits are transmitted, and this will be consequently affected by the channel. And at the receiver, the logic for the detection is If of the 3 1 bit transmitted, if at least 2 bits are 1, then that will be treated as 1, else 0. We have to find out what is the probability of error at the output. So what will the error combination? The error combination will occur when during the transmission of 3 bits of 1, there will be toggle in bits at 2 positions or at all 3 positions, the error will occur. So what are the combinations in which error can occur? When at the receiver we get the bit as 100, 010, 001, and the last case is when all the bits are toggled to 0. So these are the error combinations. For single bit, the error probability is given to be P in the question. So we have for 1 we will represent 1 minus P because P is the error probability, so probability of no error will be 1 minus P. And for this 0, 1 P will be there, and for this 0, 1 P will be there. So P square will be multiplied with probability of no error. So for this combination of error, the probability of error will be 1 minus P into P square. Similarly for this case also, as there are 2 0 and single 1, the probability of error will be same, that is P square 1 minus P. For this case will be also P square 1 minus P, and for this case all the 3 bits are in error position. So for this combination the probability of error will be simply PQ, okay, and the total probability of error will be the summation of all these 3, that is 3 times of 1 minus P whole into P square plus PQ. So this is the probability of error in the option. If we check, option A is matching. Alternatively also we can find out the probability of error by taking the combination formula. So the probability of error will have 2 factors. That is the first, when 2 bits get toggled, that is 2 bits are in error position, and the other is when all the 3 bits get toggled during the transmission, that is all the 3 bits are in error position. So 2 bits are in error position, the formula will be 3C2, that is total 3 bits transmitted. Out of the 3 bits, 2 bits are got toggled during the transmission, so 3C2, 3 combination 2, P to the power 2, 1 minus P. For all 3 bits, the formula will be 3C3. Out of the all 3 bits got toggled during transmission, so 3C3 PQ 1 minus P to the power 0, which will be simply 1. So we have simply removed that part. So if we simplify this combination, then we will get the expression to be 3P square 1 minus P plus PQ, which is same as this expression, and option A is matching with our result. So 67, answer is option A. Next question is question number 68. In this question, 4 messages band limited to omega, omega, 2 omega and 3 omega respectively are to be multiplexed using time division multiplexing, that is TDM. The minimum bandwidth of the transmission we have to find out. So the bandwidth we know is equal to half of the Nyquist rate. What is Nyquist rate? Nyquist rate will be, in this case, will be 2 times of the available frequency. So each frequency will be multiplied 2 times, and that will be summed to get the Nyquist frequency. Okay, so the Nyquist frequency will be 2 times omega plus 2 times omega plus 4 times omega plus 6 times omega. So that will be the total Nyquist rate, and half of that will give us the bandwidth. So the bandwidth will be simply 7 omega. Option D is matching, hence option D is the correct answer for question number 68. Next question is question number 69. Consider the frequency modulated signal, that is FM, is given 10 cos 2 pi 10 to the power 5 t, that is the carrier frequency is given to be 10 to the power 5 Hz, plus 5 sin 2 pi 1500 t plus 7.5 sin 2 pi 1000 t. That is, there are 2 modulating signal, that is this one and this one, are being modulated as FM by using this expression with carrier frequency is given to be 10 to the power 5 Hz. Here 10 to the power 5 hertz is the carrier frequency. Now modulation index we have to find out in this case. The modulation index beta is nothing but del f maximum, that is the maximum frequency deviation, divided by the FM, that is the maximum frequency of the modulating signal. If we find out del f max and FM, we can easily get the modulation index. The del f max is nothing but the differentiation of the phase, that is the del phi, that is the total phase with respect to t 1 by 2 pi, and maximum value of this will give the maximum frequency deviation. Now if we differentiate this delta phi with respect to t, what we will get? When we will differentiate this part, this 2 pi 1500 will come outside, so 2 pi 1500 is outside here. Similarly 2 pi 1000 will also come outside, so 2 pi 1000 will come outside, sine will become cos, sine will become cos. Now we have to find out what is the maximum value of this. This 2 pi will be cancelled. Okay, the maximum value of this will be, as both the functions are cos, the maximum value will be simply summation of their amplitude. So here the amplitude is 1500 into 5, that is 7500, and here also 1000 into 7.5, that is 7500 or 7500. 2 pi will be cancelled, 2 pi will be cancelled. So what is the del f max? Del f max is nothing but simply 15,000 hertz. Now delta f max we have found out. Now we have to see what is FM, that is the maximum modulating frequency. The maximum modulating frequency is maximum of the two frequency. Here it is 1500, here it is 1000, so FM is nothing but 1500. So FM is simply 1500 hertz. So what is the modulation index? Modulation index is the ratio between delta f max to FM. So 15,000 divided by 1500, that is equal to 10. So modulation index is simply 10. Hence B is the correct answer for question number 69. Next question is question number 70. The signal cos omega ct plus 0.5 cos omega mt sin omega ct is, whether it is FM only, whether it is AM only, or both AM FM, neither AM or FM, that we have to see. First we can write the amplitude modulated signal, that is the generalized expression, as AC whole into 1 plus AM by AC cos omega mt into cos omega ct. What is the FM generalized expression? The FM signal is given by AC cos omega ct plus beta sin omega mt, where beta is the modulation index, omega c is the carrier frequency. Here the modulation index is AM by AC and the carrier frequency is omega c, modulating frequency is omega m. Same here, modulation frequency is omega m. If we expand this expression, we will get this expression, because this is cos A plus B. We can simply apply the formula, we can simply expand this as this. Now what is narrowband FM? The narrowband FM, for narrowband FM, this part, that is the phase part, should be very small, that is close to 0 for narrowband FM. So if we simplify this expression by taking beta sin omega mt tends to 0, that is the theta tends to 0, then what will be the narrowband expression? The narrowband expression will be looking like this. Because when theta is very small, sin theta will be tending towards theta, cos theta will be tending towards 1. So this is the theta, so cos theta, this value will become 1. So this value will simply become AC cos omega ct. Now here in this expression, this sin beta sin omega mt, that is sin theta will become theta, that is beta sin omega mt. So simply AC sin omega ct will be multiplied by beta sin omega mt. So we will have this expression, that is the expression for the narrowband FM will be looking like this. Now if we multiply this AC, then we will get this expression, that is AC cos omega ct plus AM cos omega mt into cos omega ct. Now let us take a close look at both this expression and this expression. Here AC cos omega ct is there, that is the information of the carrier is present at the first part, and in the second part there are basically two multiplication factor. One factor is about the modulating signal, here sin omega mt and here cos omega mt. Only the phase is shifted here, that is pi by 2 phase is shifted, and also about the carrier also the phase pi by 2 is shifted, and AC beta will take care of the phase. Now let us take a look at the expression that is given in our question, cos omega ct. The first part is about the carrier, and the second part, if you see, the carrier signal is shifted by pi by 2 phase shift, and the modulating signal is there. So if you see, this expression is similar to this expression, as well as this expression is matching to this expression. If AC beta will take care of that magnitude and phase part, then we can say this expression can be AM signal as well as FM signal, that is the narrowband FM signal. So we cannot say that this is FM only, or we cannot say that this is AM only. We can say both AM and FM is the correct match for this expression. So C is the correct answer. Hence C is the correct answer for question number 70. Next, question number 71, 72 and 73. These are the three questions. They are having common data, and it is given that a speech signal band limited to 4 kHz and peak voltage varying between plus 5 volt and minus 5 volt is sampled at Nyquist rate. Each sample is quantized and represented by 8 bit. So the speech signal is band limited here to 4 kHz, and its voltage can vary between plus 5 volt to minus 5 volt. Okay, the speech signal is sampled at Nyquist rate, and each sample is quantized to 8 bit. Here it is to be noted that the signal is a speech signal and it is not a sinusoidal signal. The first question, that is question number 71, it is asked, if the bits 0 and 1 are transmitted using bipolar pulses, the minimum bandwidth required for the distortion free transmission. We have to find out what is the minimum bandwidth required in this case. So what are the things given? The frequency FM is given to be 4 kHz, okay, because it is band limited to 4 kHz, and the number of bits for quantization level is given to be 8 bit. So we can say that the sampling frequency Fs is equal to 2 FM, because the sampling is happening at the Nyquist rate. The Nyquist rate is nothing but 2 times the FM, so the sampling frequency Fs is equal to 2 FM, which is equal to 8 kHz, because 4 kHz is FM, so 8 kHz is the sampling rate. Then what is the bit rate? The bit rate is equal to NFS. NFS is nothing but 8 is the number of bit, Fs is equal to 8, so 64 kbps is the bit rate, and the bandwidth is nothing but half of the bit rate. So bandwidth is equal to 32 kHz, and that is what asked in the question. Or we can say the bandwidth is equal to simply NFM. N is the number of bit per quantization level, FM is the band limited frequency, that is 4 kHz. So 32 kHz is matching with option B. So question number 71, option B is the correct answer. Next part, question number 72. In the question number 72, it is asked, assuming the signal to be uniformly distributed between its peak to peak value, the signal to noise ratio at the quantizer output is. So SNR we have to find out in this pulse code modulation, where the signal is uniformly distributed between its peak to peak value. So you can simply plot the signal PDF, which will be from minus 5 to 5 for uniform quantization. That is, the PDF will have same value from minus 5 to 5 as the area of the PDF is equal to 1. So you can find out what is the amplitude by finding out its area. The area is simply 10 into, let's say B, 10B, so B equal to 1 by 10, so that the area will become 1. So the amplitude will be 1 by 10. Now what is the power of the signal? The power of the signal is nothing but X square into PDF that will be integrated. So the power of the signal is nothing but integration over minus infinity to infinity a square fx dx. So here x square fx is simply 1 by 10 and the limit is from minus 5 to 5. Here rest are 0, so the limit is from minus 5 to 5. As this is an even signal, so you can write 2 times 0 to 5, okay, and this will become x cube by 3, 1 by 10 will be there, limit will be from 0 to 5. After further simplification, we will get the signal power to be 25 by 3 watt. Now let us try to find out what is the quantization noise power. The quantization noise power formula we know for uniform quantization is delta square by 12, where delta is the step size of the quantization, okay, and the step size delta is given by 2 Vm by Q, where Vm is equal to 5 volt, that is the maximum amplitude, okay. Q is nothing but the total number of level. As there are n bit, so the total number of level will be 2 to the power 8, that is 256. So Q equal to 2 to the power n, which is equal to 256, and 2 Vm is simply 10 volt because 5 volt is the maximum amplitude. So 10 by 256, that is the delta, that is the step size. If we substitute here, we will get the noise power, that is equal to 100 divided by 2 to the power 16 into 12. So we have, this is the signal power 25 by 3 watt and this is the noise power, okay. So signal to noise ratio, we can find out S by N equal to 25 by 3 into 2 to the power 16 into 12 by 100. After simplification, we will get this expression to be 2 to the power 16 because this 3 will be cancelled, this 12 to 4, so 25 into 4 equal to 100, so 100 will be cancelled. We will have only 2 to the power 16. Now if we express this in dB, we will have 48 dB, that is the signal to noise ratio is 48 dB for the quantization used. So option C is matching, hence option C is the correct answer for question number 72. Now in the next part, that is question number 73, the number of quantization level required to reduce the quantization noise by a factor of 4 would be, we have to find out what is the number of quantization level required so that the quantization noise can be reduced by a factor of 4. So you have to see the relation between the quantization noise and the quantization level. We have the quantization noise to be delta square by 12, so delta is nothing but 2 Vm by Q. So noise is proportional to this whole square, or you can say noise is inversely related to Q square. Noise is inversely proportional to Q square, or we can write for two different noise power, we can write N by N2 equal to Q2 by Q1 whole square. In the question we have to reduce the noise power by a factor of 4, so N2 equal to N1 by 4, or we can say N1 by N2 equal to simply 4, which is equal to Q2 by Q1 whole square. Hence Q2 will be equal to 2 times of Q1. Previously the quantization level Q1, which is equal to 256, so Q2 has to be 256 into 2, that is 512, so Q2 equal to 512. So for the quantization noise to be reduced by a factor of 4, the quantization level has to be doubled, that is 256 into 2, that is 512. So option B is the correct answer for question number 73. This concludes solutions with concepts of all the questions of GATE 2008 in respect of communication subject. If you like, you may subscribe to my channel Helping Hand for EC Student to stay updated with latest video showing concept wise solutions detail of previous year questions, which will be again based on subject wise. If you have any query, you can always drop your comment in comment section. I will be addressing your query. Thank you.